Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are looking at the density of gases. Our first problem says calculate the density of water vapor at 0.909 atmospheres and 54 degrees Celsius. We are given a variation on the ideal gas equation that states that density is equal to the pressure times the molar mass, or molecular mass in this case, all over the gas constant times the temperature. Again, temperature will have to be in Kelvin. So the first thing we're going to do is convert 54 degrees Celsius to Kelvin. So let's write temperature is equal to 54 plus 273.15, which, given the number of significant figures and given that we're doing the addition rather than multiplication, we're just going to keep it to whole numbers. So that makes it 327 K. So that's our temperature. The other things we need are pressure and molecular mass. So the pressure is actually given, so we can write that over here. Pressure is equal to 0.909 atmospheres. Molecular mass, we're going to put over here because we're going to need a little more space, is going to be equal to 2 times 1.008 grams per mole plus 16.00 grams per mole, which is equal to 18.02 grams per mole. So now we have all the pieces because we know that our R constant is 0.0821 liter atmospheres per Kelvin mole. It's just a matter of plugging everything in. So pressure is 0.909 atmospheres times the molecular mass, which is 18.02 grams per mole, all over our gas constant, which is 0.0821 liter atmospheres per Kelvin mole, times 327 Kelvin. Note that atmospheres and atmospheres cancel each other out, that moles and moles cancel each other out, and Kelvin cancel each other out. So we're left with grams per liter. And what is grams per liter? Well, that's a unit for density. So we know that we are on the right track. So when you do the arithmetic out, you find that our density is 0.610 grams per liter. And that's how you solve that problem. They might have asked for a different unit, like grams per milliliter, in which case you would then convert this to grams per milliliter, just using simple dimensional analysis. Let's look at another problem that uses the same equation, but it's asking us to calculate the molar mass of the compound. So we're going to take that density is equal to pressure times the molar mass over gas constant times temperature. And we're going to manipulate it by multiplying to both sides the gas constant and the temperature, and then dividing both sides by the pressure. So we end up with molar mass is equal to density times the gas constant times temperature all over pressure. I always make sure I do my algebra separate from putting in all my calculations. This assures that I am getting the correct result. The other thing that I do whenever I'm doing these problems is I list out all my given values. So the density is given as 7.51, and it's grams per liter. That's density. Temperature is given as 63 degrees Celsius, which we're just going to add 273.15 to get it to Kelvin, which would make it 336 Kelvin. Then we just have the R value, which is all we need, and then the pressure, which is, in this case, 8.28 atmospheres. So we simply do the calculation out, and we get 7.51 grams per liter times 0.0821 liter atmospheres per Kelvin mole times 336 Kelvin, all over 8.28 atmospheres. Note that liters and liters cancel each other out, atmospheres and atmospheres cancel each other out, Kelvin and Kelvin cancels each other out, and we're left with grams per mole, which, as you know, is a unit for molar mass. So when you do the calculation out, we get 25.0 grams per mole. Now, there are several different compounds that could fit this particular molecular edit. Now, there are several different compounds that can fit this particular molar mass. So the molecular formula that they're asked to provide could be any number of things, but I like to keep it simple and look for what fits easily together. And so I've chosen beryllium oxide, but it could be any number of other things. Just make sure that whatever you do, you look through the calculations, you make sure your charges equate properly, and determine which one best fits the molar mass given.